brother Elisabio, and I'll be discussing to you the chapter 1 and the half of chapter 2 of our thesis titled Design and Simulation of Power Generating Unit by Harvesting Mechanical Energy from Opening and Closing of Swing Door. Introduction, and it will discuss about overview and background, statement of the problem, objectives of study, significance of the study, scopes and limitations. So this is the overview and background. So the Philippines, demand for electric power is increasing significantly every year with the rapid industrialization and lifestyle modernization of the Filipinos. So the conventional method for producing electricity is burning of fossil fuels, which is coals and natural gases. But burning the fuels produces hazardous flue gas, which has a byproducts of carbon dioxide, and it shows in the study that energy generating growth of the Philippines increases 5.3% from 2015 to 2020, and some alternative ways of producing energy are renewable energy, which are already available and currently being harnessed. These are wind power, solar power, and other renewable energy that are known. But there are some uncommon renewable energy resources that are not utilized, and one of those is the force exerted by a person, such as opening doors. Then, our statement of the problem is renewable energy resources such as force exerted by humans when opening and closing of doors is not harnessed. So this paper aims to design a machine that can harness the power from opening of doors. And our general objective, which is stated in our statement of the problem, the paper aims to design a machine that can convert the wasted force exerted by human from opening and closing of door into electrical energy using a DC generator. And are our specific objectives. Design and model a machine that can harvest the exerted energy during opening and closing of doors. Perform load analysis on the machine by theoretical analysis and finite element analysis using Autodesk Fusion 360. Determine the output electrical power that can be harvested. Determine the overall efficiency of the system. And the significance of the study is that it presents an alternative way of harnessing renewable energy resources, and the machine can be used on a door with people frequently passing by, and it can be a reference for other studies in the future. So these are our scopes and limitations. So the type of door to be used is a common swing door with no closing mechanism. The applied force in opening the door is 25 Newton and the angular speed is 15 rpm. These are from our related literature. The torque and angular speed will be basis of the mechanical assembly of the machine. And the intended application of this study is to harvest from the opening and closing of door. The power input will be considered to have no losses, and the power output will be determined by the generator specification considering generator efficiency of 60%. And the efficiency of the machine will be calculated by getting the ratio of power output and power input. The finite element analysis will be done on Autodesk Fusion, and also the finite element analysis will be validated through our theoretical analysis, which is we will compute. So, Chapter 2, Review of Related Literature. I will discuss the first three. The first is the mechanical design of power generator using door openings for household use. So, this paper aims to convert the energy applied by humans in opening and closing on doors. And wheel shafts, bevel gears, and the dynamo were utilized to produce power needed to charge a smartphone. And this picture shows the diagram of their prototype. Then, the input part of the mechanism consists of the wheels, shafts, and bevel gear, which is driven, basically the parts that harness the movement of closing door. The output part is the bevel gear and the dynamo. A DC dynamo were utilized to generate electrical power from the mechanical movement of closing door. And the torque applied by a person when opening or closing the door is assumed to be 10 Newton. The mechanism, the output of the dynamo was found to be 11.54 volts. The resulting voltage was tested and found to be 4.43 volts. Next is revolving doors producing green energy. So a person is assumed to waste 15 Newton meter of torque when opening a door. The energy is harnessed by rotating a dynamo to convert the mechanical energy to electrical energy. The prototype can produce 110 watts. So the picture shows their prototype, and the power produced by the dynamo is dependent on the amount of torque that the motor receives. The gears are set to achieve a lever ratio of 1:5 from the dynamo to the application of torque by human. It is found out that increasing the width of the door increases the. Next study is about energy harvesting shock absorber with a mechanical motion rectifier. So this paper presents a shock absorber with a mechanical motion rectifier that converts the two-directional motion into one-directional motion. The mechanism allows the generator to rotate in one directional at a constant speed with higher energy efficiency. So this paper aims to show the advantage of the mechanical motion rectifier. This picture shows their prototype, and the mechanical motion rectifier is inside the shock absorber. So the result shows a mechanical efficiency of 60%, and it was said that mechanical efficiency is higher with higher frequency. And that's for my presentation, and thank you.
To continue with the discussion of related literature, we have a study called a door motion energy harvesting system for powering an electronic door lock by Litwiler and Gavigan from 2014. In this paper, the researchers aims to harvest the energy that will be produced in opening and closing the swing door and to power the electronic lock. The researchers use a simple hinge-mounted rotary motor as the generator. The electricity harvested will be stored in a battery and be used to power the lock. So basically, the door lock will be self-sustaining and won't need electricity from outside sources. Also, they rectify the output voltage in order to supply DC voltage to the generator. The next study is called Potential for Harvesting Electrical Energy from Swing and Revolving Door Use by Partridge and Bachman from 2018. This paper shows the potential of swing and revolving door for energy harvesting. Knowing the initial parameters of the door and its motion, they were able to model the motion of the door utilizing MATLAB and present its equation of motion. Also, they tested different design approach for energy harvesting and compared their viability. We used some of the basic baseline parameters used in this study, such as the mass, the door width, opening force, and the moment distance of the force. The next study is called Stress Analysis on Single and Herringbone Helical Gears by Mohanrad et al. At 2019. This paper presents a comparison between helical gear design and its working characteristics through finite element analysis. The researchers attempted to identify the best suited helical gear design for stresses present on the given application. The effects of tooth bending stress on single herringbone helical gears are studied through finite element analysis and compared with the theoretical analysis. In the evaluation of the design, several stresses acting on the gear which are important in gear design performance were considered, including the tooth bending stress, permissible bending stress, contact stresses, bending fatigue strength, and etc.
Hello, this is Clarence Libaw and I will discuss the third chapter, which is about theoretical consideration. First, we have DC machine. DC machine will act as an electromechanical energy conversion device. The type of DC machine that was used is DC generator. Next, we have torque. Torque will be used since door is one of the most common application of torque in our daily lives. Since we're dealing with torque, Newton's law of motion is to be expected as well. Next, we have roller clutch. A roller clutch was used to transmit torque and allowed free rotation in opposite direction. Next, we have gears. The gears used were spur gears, bevel gears, and internal gears. As for the gear design, we used law of gearing, Lewis equation, and Buckingham equation. For the shaft design, the design will be based upon the rotational transfer of power to the gear train. Next, for the equations we used for power, we have input power and electrical power. Next, we have efficiencies. The calculated efficiencies were mechanical efficiency, generator efficiency, and overall efficiency. Lastly, we used Fusion 360 for simulation, in which we used the paint constraint, fixed constraint, and principal stresses. And that ends chapter 3.
Moreno, and I'm about to discuss Chapter 4, our methodology. So, this is our flow chart where we followed in performing the paper's objective. We started by determining the parameters of the system. Then the machine is designed based on the parameters. Basically, it was designed based on the power input and the generator's rating. The design is analyzed theoretically using the governing equation on the important components which are the spur gears, bevel gears, and the shafts. If the design of the machine can safely handle the load without breaking, the components are then subjected to finite element analysis and theoretical analysis. The theoretical data will validate the simulation. Simulations are useful to know how it will perform close to the actual. After knowing that the machine can handle the load safely, the power output based on the generator's rating is computed. Knowing the input power and the output power, the overall efficiency is computed. So this is the chosen generator, DC generator. The chosen generator was a brushless DC generator with a planetary gearbox. It is rated at 194 RPM, 12 volts, 12 to 15 volts, and amperage rating of 0.99 amperes, a torque rating of 8 kg centimeter, and a volts per RPM of 0.0523 volts per RPM. and a generator efficiency of 60%. The datasheet of the generator can be found on the Appendix Q. The working conditions were gathered from the past RRL and personal observation of the authors. The 25 Newton was adapted from the RRL found in Chapter 2, 2.5, potential for harvesting electrical energy of swing and revolving door use by Partridge and Bucknell, 2018. From the stated conditions of the power output was found, the power input was found to be 27.489 watts. Dimensions and parameters of the components can be found in Appendix C to Appendix J. And it is important to note that the power source considered here is constant. This is a video supposedly containing the animation of how the design machine works, but unfortunately my laptop cannot play and record at the same time and it's lagging, so I'm just gonna attach and send a file with the PowerPoint. For the next slide. And it's now playing. So the machine consists of a pair of spur gears where the pinion spur is compounded to the bevel gear, since the driving shaft changes direction of rotation when opening and closing of the door. A rectifying mechanism using roller clutch bearing and bevel gears was used to rectify the rotation of the generator shaft. So if it's playing smoothly, you will see that the the generator shaft rotates at one direction even when closing or opening the door. So I'll just send a link or I'll attach the video or email it to you so that you can watch, or you can watch it here at the PowerPoint. So for next slide. So this is the isometric view. Let me point out where the driving shaft is. So this is the driving shaft, this is the spur gears, and this is the bevel gears, and this is the generator shaft. So better. So this is the front view. As I said, the pinion spur gear was compounded with the bevel gears. So this is the driving shaft, this is the generator shaft. The driving shaft allows two-way rotation. The motion rectifying mechanism consists of two bevel gears and one bevel pinion. This is the two bevel gears facing up each other. So the bevel gears are set up facing each other. The bevel gears are attached with a rolling clutch bearing that locks on the driving shaft when driven on one side and rolls freely when driven on the opposite direction. The clutches are set in a way that the bevel gears will only transfer torque on one direction. The bevel gears then drives the bevel pinion, thus the generator shaft moves on only on one rotation. next slide. This is the top view. And this is the right side view. And this is the exploded view. For more detailed, for the detail of each components, please refer to the paper. It is detailed there. So for next slide. So for the gear train drive. So the generator requires at least 194 RPM. So we need a gear train that can drive the generator shaft of at least 194 RPM. So assuming that the input angular speed the door is 15 RPM. So from 15 RPM, and the spur gears have a velocity ratio of 5, and the compounded bevel gear has a velocity ratio of 3. So the resulting velocity ratio of the gear train is 15. So from 15 RPM multiplied by the 15 velocity ratio, the generator shaft can spin at 225 RPM from the 15 RPM input at the door. More detail on the used spur gears and bevel gears are found on Appendix C and D, and for spur gears you can find it on J and K, Appendix J and K. Please refer to the paper for more details. And it is important to say that we used on the spur gears module of 1.5 millimeters and 20 degrees involute heat, and the pinion has 18 teeth, and the spur gear has 108 teeth. And for the bevel gears, the bevel gear have 48 teeth, and the bevel pinion has 16 teeth, and they are 20 degrees involute bevel gears. And each face width of this bevel gears is 0.42 inches. More, and again, please refer to the appendices for the computations, design of the spur gears, and the dimensions of the bevel gears and spur gears. And there you go. There's a computation for the generator RPM, which is 225 RPM. So next, years we consider using the Lewis equation, which assumes that only one tooth of the spur gear transmit all the power. When one tooth can handle the load safely, it is safe to assume that the gear can transmit the power safely, since spur gears transmit power with more than one teeth. So for the materials, we use steel as our basis, and the properties of the steel can be found in Appendix P on the paper. And same with, so moving on, as the material of the bevel gear. The same theoretical analysis were used on the bevel gear, except that the Lewis equation is modified by multiplying a factor called the bevel factor. And this equation came from machine design Book by Kurmi. So for shaft theoretical analysis, uh, the shafts used are solid shafts. So the major forces acting on the shaft is torsion due to the transfer of torque on the gear train. So we use the solid shaft torsion equation while using the maximum torque that the shaft will experience. So for finite element analysis of the said components, I'll turn it over to Mr. Batay.
Greetings, I am Marcos Linesbat and I will be reporting about chapters 4 and 5. So chapter 4 is methodology. I'll be reporting about the finite element analysis and the determination of electrical power output and overall efficiency. So for the model of the finite element analysis for the spur gear, only the pinion was analyzed because it's the weaker link, and we use Lewis formula Lewis formula to analyze it because it is a cantilever beam. It will be analyzed as a cantilever beam, and as such, we'll only analyze one tooth of the spur. So here we can see that it uses a pin constraint, in order to revolve the spur gear. And here we can see how the load is applied to one tooth. So for the bevel gear finite element analysis using Autodesk Fusion 360, uh, the same as the spur gear, only the pinion was analyzed. The pin constraint is used for simulation. So this is the pin constraint, and this is how the force was applied to the tooth. For the shaft's finite element analysis using Autodesk Fusion 360 software, we use a 16 mm and 12 diameter shaft. The constraints are fixed. Torsion is applied to the shafts. So here is how the constraint is placed, and this is how the torsion was applied to the shaft. So determination of electrical power output and overall efficiency. The electrical power output based on the rated specification of DC generator. So we got the volt to RPM ratio using the data sheet provided for the generator, and using that we were able to get the rated amperage, and the rated amperage was used as the output current. The output power was computed using the output voltage and the output current. The datasheet provided that it has 60% efficiency. The overall efficiency for input is the input power over the output power. So chapter 5 results and discussion. Spur gear theoretical and load analysis results. We used steel for the material of the spur gear. It has a yield strength of 207 megapascals. The tooth thickness we found using the formula was at least 7.72 millimeters with a safety factor of 3. So we used a preferred width of 8 millimeters. And the tensile strength we computed was 66.592 megapascals. The allowable stress was 69 megapascals. So by theoretical load analysis, the gear tooth was safe. So for the bevel gear theoretical load analysis results, for the bevel pinion, we got a stress of 135.6594 megapascals and an allowable stress of 138 megapascals, which says that our bevel gear is fairly safe. We use a safety factor of 1.5. For the shaft theoretical load analysis results, for the 16mm diameter shaft, we have torsional stress of 21.7595 megapascals, and for the 12mm shaft, we have a torsional stress of 17.1926 megapascals, and the design stress was 62.1 megapascals. So based on the results, we have fairly safe shaftings, which is far from this design stress. This is because got the we got the diameter for the shaft using the roller clutch. So that's how the design was made. So for the spur gear results in Autodesk Fusion 360, we got a force acting on the spur pinion, which is 269.33 newtons, and tensile stress of 67.05 megapascals. This is for the stress is applied, which is at the base of the tooth. For the bevel gear results in Autodesk Fusion 360, we use an applied load of 459.2971 newtons and we got a tensile stress of 138 megapascals. This is the bevel gear, and we can see that the stress happened on the tooth base. For the shaft analysis results in Autodesk Fusion 360 for the 16mm diameter shaft, we got a stress of 21.67 megapascals, and here is how it is in the simulation. So for the 12mm shaft, we got a stress of 17.07 megapascals. And as you've noticed, the results we got in Autodesk Fusion 360 is mostly the same as the results we got from the theoretical analysis. So this shows that we got accurate results using the simulation. And that concludes my presentation.
Part of our methodology, we also compare the maximum stresses on each machine elements experiencing the highest load, mainly the spur gear, shaft, and bevel gear. As seen in Table 5.1, Comparison of Theoretical Results and Simulation Results, the maximum tensile stresses for each component calculated using FEA validates the maximum stresses for each respective component calculated using theoretical computations. This shows that the right sizes for each components were chosen, and they will be able to handle the maximum working load of the system. Calculations described in this section can be seen in Appendix B. We also calculate the electrical power output and overall efficiency of the machine. Input power can be calculated using the formula 2 pi times angular velocity times torque over 6t. Since we know the force needed to open the door, we can easily calculate the torque of the swinging door. We calculate the RPM or the angular velocity by assuming the time it takes to open the door at a 90-degree angle. Solving for the needed values, we calculate the input power to be 27.489 watts. We calculate the output power using the formula electric power equals current times voltage times generator efficiency. Note that the output power is theoretical, since we use the current and voltage rating of the chosen generator. Substituting the values in the formula, we calculate the electrical power or the output power to be equal to 6.99 watts. Knowing the output power and the input power, we can easily calculate the overall efficiency to be equal to 25.43%. I am Joben Kennard Arroyo, and I will be concluding the presentation of our thesis. In theory, the machine should be able to produce a maximum power output of 6.99 watts per input power of 27.5 watts produced when opening the door. In order to make the project viable, the torque and speed of the generator shaft should be at least 8 kg per centimeter and 194 RPM respectively. The mechanical components were designed using appropriate theoretical safety formulas and finite element analysis as presented in Chapter 5. The results have validated that the components were able to handle the maximum working load. It is therefore concluded that the design could be fabricated and has the potential for energy production. We recommend the fabrication of the machine to test the actual feasibility. Also, a full simulation of the design could also be done to further analyze the energy production considering frictional losses, rotational losses, and other mechanical and electrical losses. The use of 3D printing technology could be used to easily fabricate some of the components. Different materials for components who are under stress, such as the shaft and gears, could also be considered to make the fabrication of the machine cheaper. Future researchers could also use a different design for this kind of machine to further show the feasibility of this technology.